Every day we use dozens of electrical and electronic devices, and many times these require a transformer, which although generally we don't give much importance to it, it's the component that allows us to use electricity in a more controlled way. Since, if we connect our devices directly to a socket, we will not have good results. Furthermore, these same components make it possible to obtain electricity in our home that was probably generated dozens of kilometers away. In general terms, a transformer is made up of two or more coils of different characteristics, components that, as we saw in a previous chapter, are capable of generating a magnetic field when a current passes through them, and also induce a current when they are affected by a varying magnetic field. Understanding this, a transformer is simply made up of a primary winding, which, when receiving an alternating current, induces a continuously varying magnetic field, and a secondary winding, that when interacting with the magnetic field of the primary coil induces an alternating current output. The main result of the configuration is that we can reduce or increase the output voltage depending on how the two coils are built, in addition to allowing us to reduce energy losses considerably when we transmit electricity over long distances. But there is much more than that. In this episode we will see how a transformer works. First of all, we must understand why transformers work with alternating current and not with direct current. This occurs due to Faraday's law, which in simple terms tells us that in order to induce a current in a conductor, the magnetic field must be changing over time, either increasing or decreasing. So if we use direct current, the primary winding will generate a magnetic field that will eventually stop growing and be constant over time. And as a consequence, the secondary winding is only going to induce a current at first, but once the magnetic field is constant it will simply stop inducing a current. Understanding this, let's analyze a transformer closer to reality. During this video we will focus on a shell-type transformer consisting of a laminated core with 3 columns whose coils are wound on the central column. The position of the coils is a little different to what we had seen before, but remember that as long as the magnetic field from the primary winding reaches the secondary winding, everything will work basically the same. For now let's just focus on the coils, we will focus on the laminated core later on. In this particular case, the primary coil is the one located in the center, while the secondary coil with higher voltage is located outside for security reasons, since it is preferable to keep it far away from the core to avoid contact. One of the main characteristics, depending on the application in which we use the transformer, is the transformation ratio between primary and secondary coil. That is, how much larger or smaller is the output voltage with respect to the input voltage. This relationship mainly depends on the difference between the number of turns of the two coils, although, for simplicity, let's suppose that the quantity in the primary coil is going to be constant. If by adding a single turn we will be inducing a small output voltage, by adding a second turn we will obtain twice the voltage, since basically we will be connecting two voltage sources in series. Just like when we put several batteries in series. In this way, if we have fewer turns in the secondary coil than in the primary coil, the output voltage will be lower. If the number of turns is the same, the voltage will be the same. And if the number of turns is greater, the voltage will be higher. It's a pretty simple ratio. In fact, we can apply it in reverse. Well, if we know the input voltage and the output voltage, we could estimate the relationship between the number of turns, and furthermore, in addition to the voltage, the current output will also vary, but in reverse. An easy way to remember this is resorting to the law of conservation of energy. If the voltage increases, we have to be losing something somewhere. This conservation occurs specifically when we calculate the nominal power of each coil. The nominal power, which is measured in watts, equals voltage times current. Therefore, the only way that power stays constant and the voltage is increased at the same time is reducing the current, which also directly affects another characteristic of transformers, that is the diameter of the cables used on each coil. Because by reducing the current we can use thinner cables without worrying about them melting. In theory we could use the same diameter, but remember that less material means less weight, more compact sizes, and obviously less cost of materials for the companies that produce them. which is even more important when we are talking about high voltage transformers, so there's no point in making the wires bigger than necessary. This same difference in diameters means that in case we have a transformer in which we do not know which terminal corresponds to which coil, since they are generally covered, we could measure both resistances and deduce that the one that is smaller corresponds to the coil with the fewest turns, since, as we saw in the chapter on resistors, a greater cross-sectional area and a smaller length means less resistance. Now, getting back to the topic of energy conservation, in an ideal world, the energy delivered by the primary winding would be equal to that received by the secondary winding. However, in the real world this is not so, because there are multiple losses, such as losses in the transfer of the magnetic flux, voltage drops in conductors that make up the coil, and heat losses, among others. And it is precisely to solve these problems that a core is used in transformers, being the material that composes it the determining factor in the effect it will produce. This is due to a fundamental characteristic of the materials known as magnetic permeability, that in simple terms indicates the capacity of each material to affect and be affected by a magnetic field. To give you an idea, just by changing an air core for a steel core, the magnetic flux that will pass through the steel sections will be between 2,000 and 6,000 times stronger than with the air core, with which we will increase the induced current in the secondary coil considerably. Although keep in mind that regardless how high the core permeability is, we will never get as a result an output power greater than the input, because of the phenomenon known as magnetic saturation, in which, beyond a certain limit of magnetization of materials, it keeps getting harder to increase it further. So far it sounds pretty good. Since we increase the magnetic flux, however, when using a core we will find new problems. The first of them are eddy currents or Foucault's currents. In addition to having high magnetic permeability, a steel core is a conductive material, and even when it's electrically isolated from coils, the magnetic field of the primary coil is going to induce currents in the core just like it does on the secondary coil. Of course these currents are not going anywhere because we are talking about a metal block which forms a closed circuit, but the electrons are still going to be flowing inside, and as we have already mentioned before, a current generates a magnetic field, which by the way, according to Lenz's law, is going to oppose the magnetic field that generated it in the first place. In short, these eddy currents are going to be negatively affecting the efficiency of our transformer. But we can still do something to control them, and in fact the solution is quite simple. If we don't want there to be currents in the core, the easiest way to stop them is putting up a resistance, literally, looking for a material that has both high magnetic permeability and a high coefficient of resistivity. One of the most commonly used solutions are the steel sheets with small silicon percentages, around 4%, which are also electrically isolated from each other. That is, not only does the material have a higher coefficient of resistivity, but also its design of sheets decreases cross-section, which is another variable that increases the resistance of a component. In brief, we reduced the eddy currents as much as we could. Although it should be noted that in this process, by opposing a resistance to the movement of currents, an increase in the temperature of the material will be generated, and in fact, the higher the oscillation frequencies of the magnetic field, the greater the losses will be. The second problem we will encounter is that the amount of the magnetic flux present in the core depends not only on the amount of current applied to inductors at any given time, but also from the magnetic flux that previously existed in the core. This property is known as hysteresis, and we could understand it as an inertia of the core when changing the direction of its magnetic flux, or an energy expense that we must make for it to reorient. Luckily, the steel and silicon cores also have hysteresis losses much smaller than a common steel core, which is why they are ideal for a large number of applications, in addition to being relatively cheap to produce. However, they have a high density, which causes an increase in the weight of the transformers. Also, when working with frequencies that exceed hundreds of thousands of hertz, eddy current losses, and the temperature generated as a result of their dissipation exceed acceptable limits. For applications requiring a high-frequency alternating current source, there are other materials such as ferrite, which is a non-conductive ferrous ceramic material. That is, it is not affected by eddy currents, no matter how high the frequencies are, in addition to being less dense than steel. However, they usually have lower magnetic permeability. All this information is for reference only, because there are several alloys with different amounts of each element and therefore different magnetic permeabilities, resistivity coefficients, density, hysteresis effects, and of course, different costs as well. That is, there is no core that works for all contexts. In fact, there may be cases where we don't even want to use a core, like in Tesla coils. After having talked about all these problems and different losses that occur in a transformer, you must be thinking that they must not be very efficient in transferring energy from primary coil to secondary coil. However, these manage to reach efficiencies greater than 95%, an extremely high value compared to energy transfer in mechanical systems, where the friction between the parts generates much greater losses. But as I mentioned at the beginning of the video, transformers not only play a role in energy transformation to be able to use it on different devices. They are also extremely important to transmit power over long distances, which by the way has a close relationship with an epic battle between Thomas Edison and Nikola Tesla, and how we ended up using alternating current around the world. But clearly that will be a topic for another episode. If you consider the work I do to be worthwhile, remember that you can support me through Patreon to make more and better videos. You can follow me on my different social networks. See you in the next episode.